Hi folks, I just thought I'd take this opportunity, now that we're at the end of the second week and you've had the opportunity to look around through the site, understand what's required of the assessment, that sort of thing, to try over the next 2 or 3 weeks to present to you a number of situations which will hopefully prompt you to think about what it is we're trying to do in this unit. Now, I won't say too much at this point because what I want to happen is I want you to have the ideas that you come up with come out of the activities themselves. You'll get the idea as we go along. Now, for this one, this is our first one. Consider this. Now, when I'm doing my everyday thing, what I'm usually trying to do is to keep my eye out for things I can use as simple, cheap, everyday context that I can use for real-world starting points in activities. And it's amazing how simple they can be. This one I got because that towel there is the towel I take with me when I go to RPM and ride on a bike in the gym. And I always have to fold it to put it back, and I noticed that when I fold it in different ways, you get different results. Consider this problem that you set to some kids. We won't worry about their ages at this stage, but we'll just give them this. There's your starting point. And I'd actually have the towel to do this, by the way. I'd have a set of towels and they'd play with them. I'd say, okay, there's your starting point. Your end point is to fold the towel so that when you have it lying on the table, the two sides of the towel are like that. The first view has the lines in the towel going vertically on one side, and on the other side, if you turn it over, what you get is there's nothing there, it's just the blank part of the towel. The question is, what I'd get the kids to do is say, okay, what I want you to do is write a set of steps that someone else can follow to get from that starting point to that ending point, and then let them loose. Now what I want you to do is to stop the video, and actually, it's good if you've got a towel like this that you can play with, because any towel will do with some features on it that you can use, but have a bit of a play and see how it would work. Once you've played with it for a while, come back and start the video again. Okay. You're back. So that was the first problem. I hope you've got a set of steps that you came up with to work it out. What I would then do is work with the kids to get them to present their ideas of how to do it and see how, and I'd get them to put their solutions up on the board. I'd probably get them to use technology to do that, and they'd demonstrate their technique, get the other kids to follow their steps and make sure it worked. Then once they'd done that, and everyone's happy with that, I'd then do this. I'd say, okay, same starting point, same towel. It's a square towel with those lines on it. This time, though, the ending point of the folding activity is that. You need to be able to fold it so that both the top and bottom of it, when you put it on the table, it's a rectangle, and the lines in the towel are on both sides, the top and the bottom. The question would be, of course, you could just say, how do I do it? Or you could say, as I've developed here, how would you change the steps in the first activity to get to this result? Can you just manipulate what you already have to get this result? Or do you have to have a complete new set and throw out the old and start it with a completely new approach? Okay, stop the video and have a go at that one for a few minutes. Good. We're back again. How did you get on? I hope that you figured it all out. We're not quite finished this activity yet, so if you're working with the kids with this, you'd have to do exactly the same thing. Get a couple of the kids up to show the rest of the class what they did, see how that all goes. Then I'd do it again. You have a third one. This time the starting point is exactly the same towel, but the ending point is blank on both sides, so that the lines are actually all contained within the inside of the folds. And the same sorts of questions. This gives rise to a third result. As a result of the folding, how was this one done? Now you could use this activity, continue it on, because what you might be able to do is finish up with, depending on the class and the level you were doing it at, and understand you could do this activity in grade 1, but you could also do it in grade 8 or 9 quite successfully as a new activity, and it would still be challenging for quite a lot of the kids. The next question you could ask if you wanted to take it further is to try to get them to generalise. You know, you might get them to say, all right, what I want you to do, considering the 3 activities that we've looked at so far and the way you've got a result for each of those, what I want you to do is to write a set of instructions which you can give to someone so that it tells them how to start with this towel and produce any of the outcomes that might be possible. Right, we've given 3 here just as a way to illustrate, but what I would do is I'd have a variety of different outcomes, hopefully all of them, and go that can get any of these outcomes, and it's one set of instructions. So essentially what you're trying to get them to do is they've come up with specific things, now you're trying to get them to generalise. So that could go anywhere. Now, a couple of things that I want to raise. If we go back to the previous slide, I always gave the slides in that context, the original starting towel and the folded result in that. Why didn't I give them like that? If I gave them like that, what is the issue or issues that you're going to raise for the kids? Remember, one of the things you should know about, we don't do it in this unit over much. We did it last semester. I did at least in EDSE352, and in the science unit I had, which I can't remember now. But one of the things if you're doing anything that's got mathematics or science involved in it, one of the issues that often happens why students are unengaged, they disengage, and they just lose their interest is because you cognitively overload them. And I'd hope that you can look at this situation and understand how cognitive load is actually at play here, and why you're making the problem doing something like this a lot harder than it really needs to be. But anyway, continuing on. Second question. I can guarantee if you read the syllabus documents in relation to STEM here in New South Wales or in the national ones, there's nowhere in there that an outcome or a dot point or an elaboration talks about folding a towel. Now, the thing I want you to do is to ponder the activity and consider what syllabus and what outcome from within that syllabus could you use to justify doing that activity. While you're doing it, as you're reading the syllabus documents looking for something, consider how you might change the problem, the actual context of the problem, so it explicitly addressed something from the syllabus. It might be math, science, technology, or whatever. See if you can think of a way you can explicitly go, that activity addresses that outcome. So I'll leave you to do that for a few minutes, stop the video, and we'll come back together again. Now, continuing on, I'm wondering if you found anywhere that you might be able to do it. What I want to do from this point is to give you an explicit example that I've come up with, and there are liable to be a variety of others. But here's a maths problem. Same towel, same starting point. At this time, I tell them that the area of the towel is 1,024 centimetres squared. The problem is, I would show them that picture. I said, how would I fold the towel so that it is a rectangle with an area of 128 centimetres squared? So it's exactly the same problem as what I gave before in terms of the real world situation. I'm just taking a square towel, doing some folding and ending up with a result. But this time I'm putting in some numbers. Now, if I just ask them how I fold the towel, essentially it's the same problem. But you would be amazed how putting that in those terms makes the problem so much harder. If I ask them to actually show, without doing the problem, show me a mathematical solution which justifies, which represents and justifies what they did in the folding, it becomes a very different kettle of fish. What they're doing is taking a very simple everyday act, taking a square towel, fold it in half, and fold it in half again. And what they've got to be able to do is represent that as a mathematical process. That is no simple thing. Let's have a look at what the solution might look like. the things they would have to do, and we teach them this in maths all the time, as you're aware, we hit them around the head with it, draw a diagram. So we draw a square, we put the information on it that we do know and the information on it that we don't know. We have an area of 1,024 centimetres squared, and we know it's a square, so the sides are the same length. Because we know the area is 1,024, we can then start a process of mathematical solution to get to an answer, which is all of that. Notice here, I've got the starting area. The area of a square is side squared, so 1,000, oops, typo there, don't worry about that. So the area is side squared, get the square root of both sides, you get the length of the side to start. So the square originally is 32 by 32. I fold it once, what it will do is halve the length of a side. So it now becomes 32 by 32 on 2, which is 16, with that area. I fold it in half again, and I'm folding on the long side. So I halve the long side, it now becomes 16 by 16. That's an area of 256. I then halve either way because it's now another square, so I halve one of them. It becomes now 16 by 8, which is an area of 128. So that's the mathematical solution. That's what we expect. What I want to get across to you here is what you're looking at there is the mathematical symbolic representation of the process of folding a square towel 3 times. Now, what I want you to connect with is the idea of how complex a mathematical or scientific or computer-based representation of something which is in everyday life so simple can be so challenging for students. Now, let's continue on, see what else comes out of this. Let's think about what big ideas we might pull from this activity. What I want you to recognise initially is just consider those first 3 folding problems and the maths problem. What you are doing in each case is the exact same thing. But the complexity associated with the 2 is rather different. In what ways are they different? How hard, you know that first activity where you take a towel, you fold it in half, and then when you did it, how hard did you find it? Most importantly, what about the problem was hard? What aspect of it was hard? It had no numbers in it, there was no quantitative calculations, there was no nothing, but it's still a problem. And you still have to be able to get from a starting point and work out a logical sequence of steps to go through to get to a result. What makes it a problem is very unlike what we usually call a problem in schools. The kids know how to start it. They even know how to end it. They know what the answer is. What they don't know is how to get from the start to the finish. So that's still a problem. Next. How is the difficulty level different? How do they compare between the problems, just as a folding problem and the second one? I can tell you now that a lot of kids in year 8 or 9, if you give them that first problem, will find it really difficult. Now, the reason is the nature of the knowledge required to solve the problem is not the same as the maths problem, but there is still a knowledge base required to do it. There's a lot of work being done at the moment in America and here in Australia about spatial reasoning. Now, what spatial reasoning is understanding the nature of space and shapes and how things change from one thing into another, right? Which is exactly what this problem builds on. If you haven't had a student who understands or has had a lot of experience with just taking things like a towel and folding it and playing with it, rather than just folding it and not thinking about it, but folding it and actually considering what is happening and understanding the idea behind what happens, which is if I fold it in half across the one line, I get a rectangle, which is half the area of the original square. The dimensions of the side, one side's the same length and the other side's half the length. If I fold it again, what happens? If I fold it along if I fold along a diagonal, I change it from a square into a triangle, which is half the area of the original square, and it's the same area of the rectangle if I fold it in half on the other way. Those sorts of big ideas are mathematics, but not in the conventional sense that we think of them as mathematics. It's essentially basic reasoning. If you take someone like a builder, when it comes to doing mathematics, this sort of mathematics, which is based in spatial reasoning, they're often very good at it because they've done a lot of work. But you can take people who are good at symbolic mathematics, the traditional mathematics that we do, and they're terrible when you put them at this sort of a problem because they don't have that experience of hands-on playing with things to know how to do it. Anyway, continuing on. My question now is this. If you give kids the towel, tell them that the area of it is 1024 and say, how do you fold it to get to there, and show me a mathematical representation of the solution that you come up with, if you just hit them with that in year 8 or 9, how do you think they would go? They've got to come up with that. There are a lot of things involved before you can get to this. Remembering even the starting point is their spatial reasoning capacity to understand how to fold the towel and what happens to it when they fold it. And a lot of kids won't even have that, let alone the mathematics side of things. Now, what I want you to consider is the experiential path that students may have or would need to take to get to a problem like this, a simple everyday problem, and be able to understand what's required to do the whole thing successfully to come up with that mathematical solution. First of all, consider that they have done that first folding exercise that we did in this presentation, where they've had a lot of time spending actually folding things and seeing what happens and how areas change and how the lengths of sides change. Secondly, down the track, they follow that with experience of area. The first one is looking at area as a qualitative descriptive concept. There are no numbers involved. You don't even talk about area. You just say, you start with this and you show them what you start with, you end with that, how do you do it? So they don't actually know any formal language, any formal mathematics, but they are still developing their understanding of area, even though that's not what they know that they are in fact doing. The second step is I then took them, put them through a situation where they're working with manipulatives like blocks, you know, the old trying to put blocks in a square, and you know, you've got to change from the square into the rectangle and look at the number of blocks and then look at the relationship between the number of blocks and the dimensions of the number of blocks and dimensions on the edges and all that sort of thing. Right, so that's using manipulatives to do it. That's developing their understanding of area as a concept coming from the concrete and what the idea of area means. So we've got them that far. Next, we've got to be able to get them to a point where they can take that concrete representation of area and represent it graphically or diagrammatically and symbolically, like area is length times breadth. Being able to do it with blocks and having 3 blocks by 2 blocks and saying there's 6 blocks there does not mean they can draw a diagram with 3 by 2 to make 6 blocks. That also is something they must learn to do. Likewise, you can't have a diagram of 3 by 2 or length times breadth, put up a diagram, put L on one, B on the other, and go the area is length by breadth and expect them to look at it and just know what it means. They have to make the link, the leap from that concrete understanding to the diagrammatic understanding and the symbolic understanding. They are all different things, and they have to be able to understand that they are different representations of the same thing. Once you get them that far, that they can understand what area is length by breadth or side squared for a square, and they can do simple problems like if it's got 3 centimetres one side and 5 centimetres the other side, and it's a rectangle, what's its area? 3 5 is 15 centimetres squared. When they can do simple things like that, then you might be able to get somewhere near the new problem. But understand this, even if you've done all of those things and you've got a kid who can do all of those first three really well, it still doesn't mean they can do the fourth one. Because what the fourth one requires is all of the knowledge and understanding that they have in the first three, and they have to bring them all together in one place and understand how all three of those work together and use them in the appropriate way together to get a result. Now, one of the things we do in mathematics is a theoretical framework called SOLO. And it's an extremely good one for understanding what this is all about. This concept that we're talking about here applies in maths and science and technology everywhere. About the way we have to, the way students need to construct their knowledge to get to where they need to go. Now, considering everything you've seen here today, what big ideas do you take away from this? Where we want to go, remember, this is EDSE353 is about STEM education and approaching things in an interdisciplinary way that are based in the real world, where up to year 10, it is my view, your job as an educator is to get across to kids how the flaming world works. It's not to teach them maths, it's not to teach them science, it's to get them to understand how their world works. That's what education is for. Maths and science are the tools that we use to get them to understand how their world works. Now, in this case, what we've done is we've taken a very simple real-world concept of folding a towel, and we've then used that to be the mathematics involved in it, and we've gotten to the point where they can take that simple thing and they understand what is actually going on. Right? That's EDSE353 in a nutshell. What we'll go on with over the next week or two is I'll make a few more of these using different real-world contexts, and we'll develop our idea of what we're trying to do in this unit as we go along. Now, if you've got any ideas, any comments you want to make about it, any input you want to have, don't hesitate. It's all about ideas and what you take from this and how you might use it as the unit goes forward. Talk again in a while. Work out how to stop this thing now.